In this video, we're going to talk about valence shell electron pair repulsion, aka VSEPR, which is written right here. So what this is going to do, and at this point we've learned how to draw Lewis structures, but now we're going to talk about their three-dimensional shapes that they make, and that's going to give rise to the polarity and other impacts that we see in how matter organizes itself in the world. So some of the Lewis structures we've drawn include things like methane, which is CH4, ammonia, which is NH3, and some other molecules. And they all have different shapes when we look at them in three dimensions. So the first one we're going to take a look at is CH4, which many times when you draw it is going to look like the angles are 90 degrees. But in three dimensions, they're not really. If you have four atoms spreading themselves around a central point, the bond angle that they're going to reach if they're spread out evenly is actually 109.5. And we call this a tetrahedral geometry because if we were to put wrapping paper around it, it would have four faces. All right, so if we're looking at where the atoms are, it's tetrahedral, and if we're looking at the electron domains, it's going to be tetrahedral as well. Another molecule that we looked at was ammonia, NH3, which has three atoms bonded to the central atom and one unshared pair. So even though there's only three atoms around it, you still have the added repulsion of an unshared pair that would be right here. So your bond angle is going to be very similar to the tetrahedral shape in the last molecule, even though it only has three atoms bonded. So we would still say that it has a tetrahedral electron geometry because you have four domains. You have the three atoms bonded plus the unshared pair all repelling each other. Now the unshared pair of electrons is going to repel slightly more than the bonding pairs of electrons because they sit a little bit closer to that central atom and basically push or compress the other atoms a little bit closer together. So again, same electron arrangement, but you're going to have a different shape when we look at where the atoms are. The next one we're going to look at is bent, so water molecule right here. You would have two unshared pairs of electrons that are not shown here, but are shown in the drawing, and therefore it's going to have a similar bond angle to the last two molecules. Again, all three of these shapes so far have four electron domains. So we would say they have tetrahedral electron geometries, but when you look at where the atoms are, it looks bent. And because those unshared pairs repel slightly more, you're going to see a bond angle that's even a little bit smaller, 104.5. The next two we're going to look at are going to have three electron domains. So if we take formaldehyde right here, which has an oxygen, and it doesn't matter that it's a double bond, it still counts as one electron domain, and you have two hydrogens, they're going to spread out in a plane that's as far apart as they can get, and that would be a 120-degree bond angle, and we would call that trigonal planar. So anytime you have three atoms bonded, no unshared pairs in that central atom, you're going to get a flat trigonal planar shape, bond angle of around 120. Then we have HNO, which is a bent molecule. So like water, it is bent, but the bond angle is going to be slightly larger. And that's because there's three electron domains, given its trigonal planar shape. And again, the unshared pair is going to compress slightly more. So we're going to say that that's 118 degrees, or just a little less than 120. And then lastly, we have some molecules that are linear in shape. You can have situations where there's like three atoms, where the central point, it's a straight line across. You have bond angle of 180. So if you have two atoms bonded to the central atom and no unshared pairs on it, it's going to be linear in shape. And you can also have something like O2, the air we're breathing, or N2. And those are just, anytime you have two atoms connected, it's going to be linear. There's not really a bond angle. You don't have to say, it doesn't matter how many unshared pairs are on the atoms. If you only have two atoms, it's going to be linear as well. So these are the shapes, the different molecular and electron geometries you guys are responsible for knowing, and their corresponding bond angles.